Okay, so number 51. Hooke's law describes an ideal spring. Many real springs are better described by the restoring force. Force of spring in terms of displacement is equal to the negative k times the change in displacement minus q times the change in displacement cubed, where q is a constant. Consider a spring with k equals 250 newtons per meter and q equals 800 newtons per meter cubed. A. How much work must you do to compress the spring 15 centimeters? Note that by Newton's third law, the work you do on the spring is the negative of the work done by the spring. And B. By what percent has the cubic term increased the work over what would be needed to compress an ideal spring? Okay, so let's start out with just kind of an idea of what the situation looks like. So we have a spring and we're compressing it 15 centimeters, which is also equal to 0.15 meters. And that's really important because everything else in our equation is going to be in meters. So this is everything we know. And I am just pointing out right here that if we pull out the negative of this situation, we get this as our formula. So for A, the work done is equal to the force times displacement. And since the force changes while the position changes, we need to integrate. So this is going to be a little tricky. At least for me, integration is a little tricky. So what we're going to do is the work is equal to the integration of force times the derivative of x. And the limits are x equals 0 and x equals 0.15. So the work done is the integration from 0 to 0.15 of our force equation from up here. And the negative goes away because it doesn't matter. Dx, and then what we're going to do is we're going to add 1 to the exponents and then divide by our new exponent, and that's how we get the integral. And then we're basically just going to solve for w by plugging in these two x's. The 0 term is just going to go away because it's just 0, and we're going to get the work done is equal to 2.9 joules. Now B, by what percent has the cubic term increased the work? The values we found above are kind of the key for this part. The work value we found consisted of two parts. For the one part was the cubic term of the force, and this other part was the linear form of the force, and gives the work to compress an ideal spring. And so we want the percent increase in work from an ideal spring. And it turns out that the first half of this section right here is equal to the work needed to compress an ideal spring, which is actually 2.8125 joules. So all we're going to do is we're going to find the percent increase from this to this. So we're going to divide 0.10125, which is the difference between these two numbers, and also just so happens to be the number we got from over here, divided by 2.8125, multiply that by 100%, and we get 3.6% increase by the cubic term. And so our learning goals for this problem was Hooke's law and real versus ideal springs, as well as work. Particularly for this problem, we needed to understand the difference between real and ideal springs, because it kind of tricks us a little bit by talking about how Hooke's law describes an ideal spring, but we're actually working with a real spring. And so when we get to this part, it's like, what? I'm not using an ideal spring? So yeah, so our learning goals really focus on the spring aspect and the work needed and the difference between the work for a real and the work for an ideal spring. Thank you very much, and I hope you have a lovely day, and I hope you have a safe and healthy holiday season.